Look at this chemical equation, right? We've got sodium carbonate, which is added to calcium chloride. That causes a reaction that gives rise to calcium carbonate and sodium chloride. Now, let's break this equation down into its parts. On the left side of the arrow sign, or the yield sign, okay, that's like in math speak, this yield sign is like saying this, okay, so A plus B is equal to C plus D. That's exactly what this is. It's like a mathematical equation only using molecules, okay? So if we look at this from an equation point of view, what we end up seeing is that everything on the left side of the arrow or the yield sign, these guys right here, are referred to as reactants. They're the ingredients that are going to be mixed together to create what's on the left side, or the right side, sorry, known as your products. So your reactants mix together and they react and they produce the products. Okay? So reactants and products abide by something called the law of conservation of mass. So if we look at that, I'm going to break down from a numbers point of view what that means. So if we look at the law of conservation of mass, what we're actually talking about here is we're saying that the reactants in any reaction must always be equal, or the amount of reactants must always be equal to the amount of products. All right? Which means that you're not making any new matter and you're not getting rid of new matter. You're just rearranging it. Okay? So reactants always equal products. And the way that we actually prove that is by balancing. We can balance actual chemical equations. You'll notice here that I've got these little numbers down here like this. I got a big number out here. The reason that all those extra little numbers are there is to balance the actual equation. In our last test, you remember where we talked about MgF2? And how we had to show the ionic bonding of these two atoms? Okay, and that there was a reason that there was a little 2 next to the F, because calcium had 2 valence electrons. Fluorine only wants 1. So you can't just have one lone electron floating around there. You had to actually put in a second fluorine to take that electron. Okay? Well, the idea of the law of conservation of mass builds on that. If we look at this actual reaction, okay, let's look at this reaction, and I'm actually going to take off these numbers. Because to somebody who doesn't know much about chemistry, all right, to somebody who doesn't really know all that much about what's going on here, this could seem like a really good equation. This is like, okay, yeah, that works. When I say these words to you, you might not necessarily know what the actual chemical formula looks like. If I say sodium carbonate bonds with calcium chloride to give you calcium carbonate and sodium chloride. Okay, you could write those out in words. You might not necessarily know what they look like in terms of their chemical formula. So here, let's play a balancing act. If the law of conservation of mass tells us that the amount or number of reactants must equal the number of products or the amount of product, let's see right now, as this equation is right here, do they add up? The first thing we do in order to figure that out is we have to, number one, we have to see, okay, are there the same kinds of elements on both sides? So the first thing we want to look at is, okay, if we're going to abide by the law of conservation of mass, let's see, first of all, are we even dealing with the same kinds of elements on both sides? There has to be the same representation of the elements that are in the molecules of the reactant side. Well, they've got to show up somewhere on the product side. Let's start with, what's the first element we see there? Na. All right. What's the next one? CO. Oh, but look at this. CO, it's a capital and a capital. So is that one element or is it more than one element? So there's a carbon there. There's an oxygen. What else is on that side? Calcium. What else? And chlorine. So these are all the actual elements that are on the side of the reactants. Now let's look at the side of the products. Do those same elements appear? Do we have an Na? I'm going to write her down. Do we have a C? Yes, we do. Do we have an O? Okay. Do we have Ca? Yes, we do. What about Cl? Yes. So our first little rule here, do the same elements appear? Check. So we now know that question number 1 here has been satisfied. We have the same elements on both sides of this equation. Let's go up and add question number 2. Question number 2 is, do we have the same number of each atom on both sides? So if we look at this, do we have the same number of each atom on both sides of the equation? So I'm just going to push that up here. This is the reason that I wrote them in the same order, because it's easy to just look across the way to make sure that you have the same number. You're not sitting there and, looking this way and that, and all of a sudden, look at that. That's nice and confusing, right? Let's not make life confusing. Let's try to keep it as easy and neat as possible. So, first question. Let's look at our sodium. How many sodiums do I have on the reactant side? I've got, oops, I didn't want to do that. I've got 1 sodium. How many carbons do I have? I have 1 carbon. How many oxygens? 3. I have 3 oxygens. How many calciums? How many chlorines? 2. Okay, next thing I do, I take my tally without playing around with any numbers. I take my tally, all right, on my product side. How many calciums do I have here? Okay, so far so good. How many carbons? Awesome sauce. How many oxygens? 3. So far I'm liking this. How many calciums? How many chlorines? Oh. Now, I look at these and I say, whoa, wait a minute. There's something here that doesn't add up. It's not equal on both sides. So if I wrote this equation as it stands, this is not a correct, it's not a correct representation of what happens in nature, because it does not abide by the law of conservation of mass. Yes, it has the same elements. Awesome. But it doesn't have the same number of atoms. So here's where we have to take a few liberties and we have to try and balance things out. Okay? The question is, do we just add a bunch of little subscript numbers? Unfortunately, you don't add subscript numbers, okay? And I'm going to kind of break my rule here because I will add one in a little bit. But when you're balancing equations, all right? When you're balancing equations, you normally are not allowed to add these little subscript numbers on the back. Usually the only thing you can do, and these rules, the rules of balancing equations, are exactly like the mathematical rules of exponents. These little numbers here behave like exponents do in math speak. Okay? So if I look at this, if I have 1 Cl here, but I need 2 on the other side, I can't just add a little number 2 here. I'm not allowed. So what is it? What is one thing I can do? I can add a big number 2 over here. And actually, I'm going to do that in a different color. I can add a big number 2 here. But the problem with that is that, sure, my chlorine now has 2, but what else has 2? My Na, because like in exponents, whatever's in the front of the bracket here gets multiplied by everything inside. So now I get 2 NAs and I get 2 CLs. So my CLs work out, but this is not good. I have a problem with my NAs now. So what can I do on my reactant side to make sure that I've got 2 sodiums? I can add also a big number 2 here. But then, this is getting nice and messy. Wait for it. It's actually not as bad as you think. It's actually not as bad as you think. Now, having 2 of these means that I've got 2 NAs. I now will have 2 times C, and I will have 2 times O3. So my NAs go up to, notice how I'm not erasing my numbers there. I'm just putting a line. That way I can see my progression. Okay, I can see all the changes I've made. So now what do I do to my C's? 2. O would be 6, not 5. It would be 6 because it's like multiplying an exponent by a whole number. Okay, so here it ends up being you've already got 3 O's. Well, 2 times 3 O's is 6 O's. Well. Now, remember how I told you? That you don't add little subscripts? You're going to. Well, if you were given this question on a test, the little subscript would have already been there. Okay, the little subscript would have already been there. In order to balance all of this out, had you been given this question on a test, you would have had a little 2 here already on the outside of this bracket. Which means how many C's would you have on this side? You would have 2 times, because this little 2 gets multiplied by this, and the little 2 multiplies by this. Had I written this equation out and asked you to balance it, what I would have done would have given you something like this. I would have put a little blank here, and I would have put NaCO3 plus, I would have put a line here, CaCl2 yields Ca bracket CO3 2 plus, and I would put a little line there in case, NaCl. All right, the little lines imply what you're allowed to do. Notice how I told you that you're not allowed to add these little subscripts. And we added one up there. That's why in a real question, that subscript would have already been there. So we would have already started off with 2 C's on this side, on the product side, and 6 O's. And then you would have just had to add the big 2 over here to balance it out on the reactant side. So this balanced equation, when we actually make this precipitate, if you were to write up this perfectly valid chemical equation for this reaction, you would get 2 molecules of NaCO3 plus 1 molecule of CaCl2 yields 1 molecule of CaCO3, bracket 2, right? Plus 2 molecules of NaCl. Now notice how I put the ones there. You don't have to. You can leave that blank. It means the same thing. Okay? When you multiply something by 1, it's just that something. Well, this is the same thing. Okay? So this is the perfectly balanced equation down here, and this abides it answers our two questions wonderfully. Are all the same elements on both sides? Yes, they